Trig substitution. In this section, we're going to do something that's like substitution, only it's backwards. And so I call this thing reverse substitution. Okay? Now, in substitution, when you have an integral, right, like x e to the x squared dx. You don't have to write this down. This is just kind of scribbling at the top of the page. And we use a substitution like u is equal to x squared, and we do u is 2x dx. So we put the 2 in, and we pull the 1/2 out. Okay? That's normal substitution. So what are we doing? We're finding something in here that we want to be u, and we're writing u as a function of x, right? And then we're finding du, and we want then du to show up in there. And we're turning this thing into something in terms of u, e to the u du, right? So we find something that's an expression of x, and we're going to replace it with a u, but then we also have to replace the rest of the stuff with the du. Okay? Reverse substitution is actually easier, but there's no guarantee that whatever it is that you choose makes your life simpler. Because here's what reverse substitution says. I'm going to take and find some function of another variable, t, and I'm just going to replace x with a function of t. So I'm starting with an integral f of x dx. And I'm just going to, everywhere there's an x, I'm going to put some expression that depends on another variable now. Instead of trying to find, a group of x stuff together and replacing with u, I'm just going to plug in for all the x's a different function. Okay? And then I can just replace dx with g prime of t dt. That's an easier substitution to do, but most of the time it doesn't make your life easier unless you're smart about what you choose your g to be. So here's what we've got. Integral f of x dx becomes the integral of, everywhere there's an x you put g of t, and everywhere there's a dx you put g prime of t dt. So I look at this integral and I see this 1 over the square root of 16 minus x squared. I notice kind of looks like 7.2. It's got some similarity to one of these guys. Like the 1 minus something squared. It's something minus something squared. Okay? So here's my thinking. Follow me on this and see if this doesn't work. Back to here on your notes. First of all, let's get it so it looks even more like it by taking out that 16. All right, so let's write this. The integral of 1 over square root of, if I pull a 16 out of both of those terms, what do I have? I have a 1 minus 1/16 x squared. Dx. Okay? So now if this here was a sine squared of theta, then notice that would mean I would have on bottom the square root of (16) times 1 minus sine squared of theta, right? But what is 1 minus sine squared? It's cosine squared. So I've got the square root of 16 cosine squared of theta, which is, oh, I'm sorry. Yes, absolutely. My bad. Square root of 16 cosine squared. 4 cosine. Which is nice and pretty simple in the denominator. So that would work if 1/16 x squared was sine squared of theta. So what choice of x gives me that? So if I take 1/16 x squared, I want that to be sine squared of theta. Now if you just take the square root of both sides, what do you have? Square root. 1/4 x equals sine of theta, or x is 4 sine of theta. And I switched to theta just because I'm talking about trig, but that's the same as if I'd used the t, up here. Don't let the t versus theta confuse you. So here's a good choice, or here's a possible choice, of replacing x with 4 sine of theta. Because if I do that, then 1/16 x squared gives me a sine squared. Okay? Now, I'm going to jump ahead just a second. What I'm going to tell you later on the next page at the bottom of it, is when you see a square root of something squared minus x squared, a good choice for your substitution is x equals a, whatever the thing being squared is, so the square root of, in our case, 16, sine of theta. So this table right here gives you your best guess, but I've kind of given you a reason of why that would work. In our case, I would choose x equals 4 sine of theta, and then that turns the bottom into something very simple. Okay, so now I'm going to do a couple of things here. I just want you to follow me. First thing I want to do is I want to solve for theta. The first thing I did over here was solve for x. I want to be able to do both. If I solve for theta, all I have is that theta is the inverse sine of x over 4. I just move the sign to the other side by taking the inverse sign. That's going to come in handy in just a minute. I'm just planning ahead. But I need to have this thing solved for x so that I can also do dx. If x is 4 sine of theta, then what's dx? You're going to have to make some flashcards. So I went the wrong way, didn't I? You did. Derivative of sine is cosine. Derivative of sine. In fact, I'll tell you what, whenever I try to remember these things, that's the one phrase I remember. I don't remember all the rest because I can get to all the rest of them if I remember that fact. The derivative of sine is cosine, which means that the derivative of cosine is the negative one, right? And the integral of sine is the negative one. But the derivative of sine is cosine, so I remember to keep those two positive. Yep, you do. Got to practice it. 4 cosine of theta d theta. Okay. So here's what I know. In the original problem, if I replace x with 4 sine theta, the denominator becomes 4 cosine theta. The whole denominator, right? Square root of 16, 1 minus sine squared gives me square root of 16 cosine squared, which gave me 4 cosine theta. So here's what this integral now looks like. It's the integral of 1 over 4 cosine theta times, and dx. What is dx? 4 cosine theta d theta. Isn't that nice? The 4's cancel. The cosines cancel. So I have the integral of 1 d theta. Theta plus c. But I'm not done because the original problem had what variable? So I need this in terms of x. So what is theta in terms of x? Sine inverse x over 4 plus c. Just like kind of all fell together there at the very end. It's nice. As long as you figure out which one to choose here along the way. Now, it's not always going to be as neat as everything just falling out. Sometimes you get to this point and you got to do the things we did from 7.2 to integrate trig functions. But a lot of times that's where things just fall together. You got the right choice here, okay? So when we see square root of a number minus x squared, like the square root of 16 minus x squared showed up in my integrand, then I'm going to substitute x equals a sine of theta, and then use the identity that when I have a 1 minus sine squared of theta, I can replace it with cosine squared of theta. Okay, so that's my clue. When I see square root of something minus x squared, that's something, right, the 16, I'm going to take the square root of that. In our case, I used x equals 4 sine theta. Everybody see how we get from the 16 to the 4? So instead of trying to reverse engineer this or think it through from the very beginning, what's the obvious choice based on what I just told you for the substitution on the next problem? Let x equal 3 sine theta. Right, because you see a square root of something minus x squared. So by my suggestion, we're going to now replace this with a squared is 9, which means a is 3. So that's how we get the x equals a sine theta. We're going to use 3 sine theta. Yeah, so let's do this. In fact, we should do it both ways every time. Once this thing is solved for x, let's solve it for theta before we do anything else. So that's x over 3 equals sine theta, which means theta is the arcsine or inverse sine of x over 3. But we also need to do dx after we've done the solve for theta. So find dx. dx is 3 cosine theta d theta. All right, so what I do next is I simplify the radical. So I chose my substitution, I solved for theta, I found dx. Now I'm going to simplify the radical, which means I want to look at what is square root of 9 minus x squared, just that piece. That's square root of 9 minus 3 sine theta squared, which is square root of 9 minus 9 sine squared theta. You see what I'm doing? I just plugged in for x, my substitution. Now what can I do? Well, I gotta factor it before I can just square root each part, right? Because you can't take a square root of different pieces of a subtraction. You can only do it if they're multiplied together. So pull out the 9, and what are you left with? 1 minus sine squared, and now that's where we use our identity. 1 minus sine squared is cosine squared. And now it's 3 cosine theta. So now we try the full substitution. We plug in for all the x's, 3 sine theta, and we plug in for the dx, 3 cosine theta d theta. So what does my integral now look like? The top, I've already simplified, is right, because the integral of square root of 9 minus x squared turned into 3 cosine theta. What's in the denominator? Square both of it. 9 sine squared theta. And then dx, 3 cosine theta d theta. Not quite as nice little cancellation as what occurred before, so now we got to do some work with our trig.
So can you multiply the no, you
Yeah, you can. I would. At least, let's see what happens if we do. We get 9 cosine squared theta divided by 9 sine squared theta d theta. So what can we do there? First thing is cancel the 9s. Now what? Okay. Yeah. What trig function is? Cotangent. So this becomes the integral of cotangent squared theta d theta. And to me, this is where having a derivative and trig identity cheat sheet becomes helpful. Because if you pull one of those out, there's a couple things that will stand out to you. This is just some trig identity stuff. One is that I think it's 1 minus yes, actually it's the other way around. That cotangent squared of theta is cosecant squared of theta minus 1. And by itself, it doesn't look like that helps much, but there's also a formula that says that the derivative of cotangent squared of theta is negative cosecant squared of theta, or the integral of cosecant squared of theta is negative cotangent squared of theta. All of these would appear on one of those tables. And if you stare at that for a second, you realize how that might help. I can't actually take the integral of cotangent easily. But just like with tangents and secants, I can't take the integral of tangent squared, but the integral of secant squared is easy because secant squared is the derivative of tangent. That's what's happening with the cosecants and the cotangents here, right? If I can turn this into cosecant squared, then I can use the fact that I know the integral of cosecant squared is just a negative cotangent. And that's not squared. That's my error. This should not be squared there. Sorry. I should say the derivative of cotangent is negative cosecant squared, and the integral of cosecant squared is just negative cotangent. Okay? So that's my little trick, is to use the identities to get me to something I can integrate. Namely, I can do integral of cosecant squared of theta minus 1 d theta okay, by trig identity. And then what I just told you, what is the integral of cosecant squared? Negative cotangent. What's the integral of minus 1? Theta. So minus theta plus c. But you got to have your answers in terms of x. Okay. So far, we've done a substitution. We turn it into something that we can integrate once we apply a trig identity to it. I could plug in theta. I know what theta is from up here. Problem is now, what is cotangent of that theta? Now, I could write cotangent of the sine inverse of x over 3. But that's not a very good answer because we can actually do better. Going back and remembering what our trig functions mean. Okay? I want you to look at something with me. Okay, the last step here is to build the triangle. And what do I mean by build the triangle? This statement right here that I'm going to put a green box around. Do you remember that sine of an angle is, in terms of a triangle, do you remember these terminologies? Opposite over adjacent. SOHCAHTOA, if you've learned, right? Sine is opposite over hypotenuse. Sorry, I meant hypotenuse. Tangent is opposite over adjacent. Cosine is adjacent over hypotenuse, right? SOHCAHTOA. You're going to need to remember that. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. And tangent is opposite over adjacent. So down here on my triangle, I'm going to draw, I'll do this in red. I'm just going to draw a random right triangle and put the theta right there. So, sine is what? What did we decide sine was? Sine of theta is x over 3. So that means the top is the opposite, the bottom is the hypotenuse. So opposite of sine is x, hypotenuse is 3. What does that make the remaining side? The square root of that, right? Remember, a squared plus b squared equals c squared. So in our case, something squared plus x squared equals 3 squared. If you move that to the other side, that something becomes the square root of 3 squared minus x squared. Yep. Notice that's exactly the thing that we had in the integral. But that's just from the Pythagorean theorem. Okay, so if that's the case, then what is cotangent? Cotangent is cosine over sine, but it's adjacent over hypotenuse. No, over opposite. You were right. You said it right. I said it wrong. Adjacent over opposite is cotangent because it's the flip of the tangent. So what is the adjacent over the hypotenuse, over the opposite in this triangle? Square root of 9 minus x squared divided by x. Okay? That's adjacent to theta over the opposite. And then what's theta? We said before was sine inverse of x over 3 plus c. That right there is the antiderivative of your function. That's your integral. That's what a typical, regular old trigonometric substitution problem looks like. Don't you love it? Isn't it fun? All right, that took all my time, so I have to stop there. We'll do more examples next time. The good news is, well, partially the good news. The steps are the same for other problems. You just start with a different substitution depending on whether you see square root of 9 minus x squared, square root of x squared plus 9, or square root of x squared minus 9. There's 3 different choices that will show up. Okay? And so you decide based on this table below which one you're going to substitute. Where things get hairy is not the end. The triangle is actually the same problem every single time. You'll do it the same way every time. The replacing and simplifying the integrals the same way every single time. Where things get messy is once you get to right here. And you'll have to use whatever you can come up with to try to integrate the trig. That's why we needed 7.2 in this. Okay, I'm done. We'll come back and finish this on Friday. I owe you 3 minutes now.
3? I don't think so. You went us like 2 or 3 minutes over last time.
So I owe you like 5 minutes now?
Oh, you owe us? I thought you said you were going to, as in we're going to stay for X.
No. I owe you 3. I got to let you out 3 minutes early one of these times.
Oh, okay.
Remember to balance it all out.
It's
So
about
that,
5 or so now.
okay.
We got out a little late.
Ugh.